In this video, let's go ahead and take a look at 10 different practice problems that deal with Algebra 1 concepts. And while I'll have some other different sets of practice problems that deal with calculator-based questions, these particular 10 questions are going to be non-calculator practice problems. And real quick, if you'd like to download a free copy of this blank PDF or answer key PDF, you can find a link to that in the description box below. Alright, let's get started. For number one, we're being asked to find all the zeros for this given function, right? Now, if we take a look over here, whenever you have a linear part of this function, like this one here, this x minus 4, if you set it equal to 0, then we can see here that x minus 4, if we set that equal to 0, if we add 4 to both sides, then x would equal 4. That would be one of the zeros. That means that if x was 4, then f of x or f of 4 would be 0. So that's going to be one of the zeros for the function. So if you see a linear factor term, go ahead and start with that. Now over here to the right, this is a trinomial, so this part is quadratic. You're going to have to go ahead and factor that, okay? So if you need to factor this, one thing I like to do here is just take the coefficient for the first term, which is going to be 1. And so I know the factors of 1 are just 1 and 1. And the factors of negative 24 that add to get to this negative 5, I'm going to go with negative 8 and positive 3. Right? So if we multiply here across 1x times negative 8 is negative 8x, 1x times 3, that's going to be positive 3x, negative 8x plus 3x is negative 5x. So this is actually going to factor into 1x minus 8 multiplied by 1x plus 3. Okay. Now we're going to set this equal to 0 because, again, we are looking for zeros here. And so if we set this x minus 8 equal to 0 and we go ahead and add 8 to both sides, then that's going to be saying that x would equal 8. And so that if x was equal to 8, then f of 8 would equal 0, or the y value would equal 0. Over here, this x plus 3, if we set that equal to 0 as well to see what would make this linear binomial equal 0, we could take away 3 from both sides, x would equal negative 3. So if x was negative 3, then y would also equal 0 here. So what are all the three zeros for this particular function? Well, this is a cubic polynomial. It's going to cross the x-axis at 4, 0. It's also going to be crossing it at 8, 0. And finally, it's going to be crossing it at negative 3, 0. If you're curious what this might look like, we could look at this on a coordinate plane, and if negative 3 was a little over here to the left, and then positive 4 was over here to the right, and then positive 8 was more to the right, maybe something like this. If we sketch this polynomial, it would be a cubic one, and it would look something like this, where we would come up on the left side, then come down through this point of 4, 0, and it would come back up. So just a rough sketch, nothing too accurate, but this is what this polynomial would look like. And if you find out when, what x values make this whole thing equal to 0, which we just found 3 of them, those would be the zeros of the function. Here is number 2. The question is the sum of two rational numbers sometimes, always, or never rational? Well, if we're going to add two rational numbers, remember rational numbers means you can write it as a ratio of two integers. So maybe something like this. If you had a rational number like 4, if we add that to another rational number like 3/5, right? Well, if you add those together, you're going to get 4 and 3/5. Just adding those fraction and whole number. And if you write this as an improper fraction, that would be 23/5. And that's a ratio of two integers. So this is definitely rational. I guess if we try to think of something else, what about if it's like a decimal, right? Maybe something like 4.3. If you add, I don't know, something like 1.1 to that, what's that equal to? Well, that's 5.4. So I guess the question is that rational? Well, as a mixed number, you could write this as 5 and 4/10. And then as an improper fraction, that's going to be 54/10. So is this a ratio of two integers? Well, yeah, so this is still going to be rational. I guess what you can do is think about if there are other options, whether they're fractions or decimals, but as long as they're rational, so if it's a fraction or a decimal that you can write as a ratio of two integers, if you add them, you're always going to get something that is going to be rational. So we're going to go ahead and say always here, and you can come up with some other maybe examples to see if that is true or not, but it should always be rational. All right, for number 3, the question here is the product of two irrational numbers sometimes, always, or never rational? And provide some examples. So let's think of an irrational number, something like a non-perfect square, so maybe the square root of 5. If we multiply that by maybe the square root of 5, that's also irrational. Now that is going to equal the square root of 25, which is just equal to 5. So in this case, this is going to be rational, right? But is that always going to be the case? Well, let's see. If you take maybe the square root of 3 and you multiply that by the square root of 4, that's going to be the square root of 12, right? Now the square root of 12 is going to be irrational, so that's not rational. So you can't say it's always, and you can't say that's going to be never. So looks like we have two examples of one or the other. You could also say something that's irrational would be like pi, right? If you multiply something like pi by another pi, two irrational numbers, that would just be pi squared, and that would still be irrational. So in terms of this, if we can say that it's rational sometimes and it's irrational sometimes, then we're going to go ahead and say that it is sometimes going to be rational. Here's number 4. For number 4, the question is, if a quadratic function is factorable, then are the zeros sometimes, always, or never rational? Okay, so let's think about a quadratic function that is factorable. Maybe something like this, where we have f of x is equal to x squared plus 5x and then plus 6. So is this factorable? Yeah. If you go ahead and factor this, this is going to be the quantity of x plus 3 times the quantity of x plus 2. So that is a quadratic function that is factorable. So what would the zeros be here? Well, if you take a look at the 0 over here, then if you set that equal to 0 and subtract 3, then at x equals -3, that would be a 0. And over here, if you set this equal to 0, then at x equals -2, you'd have another one of these zeros, or x-intercept. So I guess the question is if it's factorable, are the zeros going to be rational? Well, this -3 is rational, and this -2 is rational. And each time, if it's factorable, you're going to be getting some sort of fraction or whole number or integer as one of your zeros. So you can go ahead and try a couple different examples. I can try another one here. If you have another function that is factorable, so let's see, x squared, I don't know, minus 4x, and you can also say like minus 12, right? So is this factorable? Well, this would end up factoring into x minus 6 and x plus 2. If you need to pause to think about that, feel free. But if it is factorable, then if we take a look at the zeros here, then this one would be x equals positive 6. That would make this function equal 0, or the y value, or at x equals -2. So both of these zeros are rational. So you'll find that if you can factor a quadratic function that's in standard form and write it into factored form, then we can go ahead and say that you're always going to have zeros that are rational. All right, for number 5, the question is to rewrite the quadratic function in factored form and then find the zeros. Okay, so right now it's in standard form. I'm going to go ahead and look for some factors of this -10. So factors of -10, I'm going to go with maybe -5 and +2. If I need to change the signs, I will in a moment. Maybe factors of -21. I'm going to put a 7 and a 3, but one of them's got to be negative. So I'm going to go ahead and make the 3 a negative for now and see what happens here. If I multiply across here, this will be -35x, because again, that's -5x and +7. So that's -35x. This would be -6x. -35 plus -6, that is -41x in the middle. So this helps me kind of find what my binomials are going to be. So the products of those and the sum of those will help us out a little bit there. So I'm going to go ahead and open up some binomials here. Now, what paired here was the -5x plus 7. So I'm going to put this -5x, and then I'm going to put the +7. So these are going to be paired up as the outers. Okay, so when we FOIL, they're going to multiply by each other. And this is going to be 2x and -3. So I'm going to go ahead and put the 2x at the beginning of this binomial, and then the -3 here. So if you were to go ahead and multiply this out, the binomials, this would get you -10x squared, right? That's the first. The outer would get you this -35x, which is what we had over here. The inners would get you -6x, which is what we had right over here. and the last here would be negative 21. And if you go ahead and add these middle two terms here, you're going to get negative 10x squared minus 41x minus 21, which is what we were looking for when we had this in standard form, right? So this would be the factored form. What you could do, maybe just to go a little bit further here, is look inside here and see that we have a negative that we could factor out. So I think the factored form finally would be take out a negative here, and then this would be 5x plus 3, just because we like to have positive coefficients in the beginning, and then this would be 2x plus 7. Now, the question is say to find the 0, so we should go ahead and set this equal to 0. So what would that be here? Well, if we go ahead and set this equal to 0, this would be 5x plus 3 would equal 0. Take away 3 from both sides, that would be 5x equals negative 3. And if you divide both sides by 5, that would be x is equal to negative 3/5. All right, so that would be one of our zeros. It would be at negative 3/5 comma 0. That's where this quadratic function will cross the x-axis at one point. And then over here, this helps us find another one. So 2x plus 7, set it equal to 0. Take away 7 from both sides. That's 2x equals negative 7. Divide both sides by 2. X equals negative 7 over 2. So that means that at negative 7 over 2 comma 0, that would be our other 0, or where the quadratic function or parabola crosses the x-axis. All right, here is number 6. For number 6, we're going to go ahead and simplify this polynomial expression. Keep in mind that when we are subtracting, we need to know that there is going to be an invisible negative 1. So in front of the second parentheses, really there's this negative 1 that's going to be distributed amongst these two terms inside here. So expanding this, we're going to have 2x to the 4th power minus 5x to the 3rd power plus 1x. I'm just going to write x though. This is minus 4x cubed. Okay, because it's negative 1 times positive 4. And then this is going to be plus x to the 4th power, because it's a negative 1 times another negative 1 that's kind of hanging out over here. That gets you a positive x to the 4th power there. Now we should probably write our answer in standard form, so let's go ahead and combine the terms that have the same highest power here. So 2x to the 4th plus 1x to the 4th, that's going to be 3x to the 4th power. And then this negative 5x cubed minus 4x cubed, that's going to combine to make negative 9x to the 3rd power, 9x cubed. And then finally we have this 1x here. It doesn't have any like terms, so we can just go ahead and write plus x. So this would be the most simplified version to write this polynomial expression. Here is number 7. So for number 7, we're going to go ahead and add these two pieces together here. Now, it's kind of nice when we have a plus sign here because we're just distributing a positive 1, and by the identity property of multiplication, nothing's going to change there. So just be careful when you have a minus sign. So here we're going to write 3x to the 3rd power minus 7x squared, and then plus 1 times 6 is just going to be 6x squared, and 1 times negative 5 is just negative 5x cubed. Okay, starting with the highest power, we have 3x cubed minus this 5x cubed. So 3 minus 5 is negative 2. So our leading coefficient is negative 2. So negative 2x cubed. And then we have two like terms here of negative 7x squared plus positive 6x squared. Negative 7 plus 6 is negative 1. So I'm just going to write negative x squared, even though there's an invisible negative 1 there. But this would be the simplified polynomial. All right, here is number 8. For number 8, Chipotle Middle School is selling tickets for their school musical titled The Beautiful Burrito. On the first day of ticket sales, 3 adult and 9 child tickets were sold for $75 in total. I'm going to go ahead and write a linear equation for that. So I'm going to have 3 adult tickets, so it's going to be 3x. X will be my adult tickets. 9y, y will be our child tickets, and that would be a total of $75. Okay. On the second day of ticket sales, it looks like 8 adult tickets, so that's going to be 8x, because again, x is a number of adult tickets, and then 5 child tickets, so it's going to be 5y, 5 of those, and that totaled $67. Okay, it says write a system of equations, so just went ahead and did that already. That's our system, and then we're going to go ahead and see if we can find the price of 1 adult and 1 child ticket. So basically, find x and find y. So you could solve this by graphing. You could use, substitution or elimination. I think because all of our coefficients are, not the nicest, it kind of makes the most sense to use elimination here. So I'm going to go ahead and see if I can get these, terms or coefficients rather to match here. So I'm going to make this 3x and 8x have the same leading coefficient, or opposites rather. So I'm going to multiply this top one. Let's go ahead and multiply it by 8. And I'm going to go ahead and multiply this bottom one by 3. Okay, that way we just have the same leading coefficient, and we can add or subtract these two linear equations. Okay, so 8 times 3x on top, that's going to be 24x. 9y times 8 is going to be 72y. And then 75 times 8, let's see, I think 75 times 2 is 150, so multiply that by 4. I think that's going to be 600. Then on the bottom equation, 3 times 8x, that's 24x. 3 times 5y is going to be 15y. And then 3 times 67, well, 3 times 60 is 180. 3 times 7 is 21, so I think this is going to be 201. Okay, so we have these matching coefficients of 24x and 24x, and you can go ahead now and just subtract these two equations from each other. So 24x minus 24x, those go ahead and just get eliminated. Then 72y minus the 15y, that's going to be 57y. And then on the right side there, that's 600 minus 200. I believe that is going to be 399. All right, finally, what we're going to do is divide both sides by 57. If we do that, we're going to get y is equal to 7. And again, 7 represented the cost of one of the child tickets. So we're going to go ahead and say that each child ticket is going to be $7. And then we can go ahead and take this y equals 7 and substitute it either into this bottom equation here, or we can substitute it into this top equation here to solve for x. I'm going to go ahead and choose the bottom one there. So if I go ahead and choose this bottom one, I think that's going to be 8x plus, let's see, 5 multiplied by 7, and that's going to be equal to 67. Okay, so 5 times 7 is 35, so it's going to be 8x plus 35 is equal to 67, minus 35 from both sides, x is going to be equal to 32, and dividing both sides by 8, x is going to equal 4. So based on x equaling 4, we can go ahead and say that each adult ticket would be $4. Alrighty, so that is number 8. Let's check out number 9, see what's going on for this problem. So for number 9, given the linear equation f of x is equal to negative 3x plus 5, let's go ahead and determine the linear function g of x if g of x is equal to k times f of x, where k is equal to negative 4. Okay, so let's go ahead and see what we're going to do here. So we know f of x, this is equal to this negative 3x plus 5. So that's a linear function. And what we're going to do is we are going to multiply this whole thing by k. All right, so what we're going to do on the left side is we have k being multiplied by this f of x. All right, and so on the right side, we should also multiply this k by our function. All right, so this negative 3x plus 5, that is our function here. Now we are being told in the problem here that we do know that k is equal to negative 4. So we just have to take negative 4 and just basically multiply our function, or f of x, by that negative 4, right? So if k is negative 4, we're essentially going to take this negative 4 and multiply it by our function, which is just f of x, or this negative 3x plus 5. So all you got to do is go ahead and distribute this negative 4 to both of these terms inside here. So if we do that, we're just going to be getting 12x, and then let's see, negative 4 times positive 5 is going to be negative 20. And so this is going to be that negative 4 times f of x, but that's really the same thing as k times f of x, which we're being told is g of x. So we can go ahead and say here that g of x is equal to this 12x minus 20, and that would be another linear equation. And finally, here is number 10. For number 10, we're going to take a look at two different functions. The first function is going to be f of x is equal to negative 4x plus 3. So this is a linear function. And then the second one is g of x is equal to 2x squared minus 7x plus 5, and that is a quadratic function. We need to go ahead and determine the product. We're going to multiply f of 3 and g of negative 2. Okay, so let's go ahead and see this first one. So this f of 3, that's really only going to be talking about this top function over here. So let's maybe focus on that one. So we know f of x is equal to negative 4x plus 3. So what's f of 3? So f of 3 just means we're going to change x to 3, or substitute it. So it's negative 4 times 3 plus 3. Negative 4 times 3 is going to be negative 12. Negative 12 plus 3, that's going to be negative 9. So f of 3, that's equal to negative 9. And then secondly, we have to figure out what g of negative 2 is. So let's go ahead and just apply that to our quadratic function over here. So if we do that, that's going to be, let's see, we know it's going to be g of x, the original function, is 2 times x squared minus 7x plus 5. We just want to know what's going to happen if x is negative 2. So let's do g of negative 2. That's going to be 2 times this negative 2 squared minus 7 times negative 2, and then plus 5. Now let's see, negative 2 squared is going to be positive 4. Positive 4 times 2 is going to be 8. And then we have negative 7 times negative 2, so that's going to be positive 14. Then we're going to add 5. Now 8 plus 14 is going to be 22. 22 plus 5 is going to be 27. So to find the product between these two values, let's just go ahead and take that negative 9, and let's multiply that by the 27. Let's go ahead and just multiply these two. And when we go ahead and multiply negative 9 times 27, that's going to be negative 243. So that would be the product of f of 3 and that g of negative 2. So there you have 10 different practice problems dealing with some Algebra 1 concepts. If you found the video helpful, please consider giving it a thumbs up and sharing this as a resource to maybe a classmate or friend who might also find it helpful. And as always, keep up the great work that you're already doing, and I'll see you in the next one.